This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss the solutions, relevant concepts, and scoring guidelines associated with some of the parts of our 2020 mock AP Calculus exam, Form BC, Question 1. My name is Steve Kokoska. I'm a recently retired professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Form BC Question 1 involves the graph of g prime, the derivative of a twice differentiable function g. The graph of g prime has exactly one horizontal tangent line in the interval -1 to 10 at x equal 4.2. The plane region R is in the first quadrant and is bounded above by the graph of y equal g prime of x, below by the x-axis, and on the left by the y-axis. And we also know that g of 0 is equal to -7, g of 9 is equal to 12, and the definite integral of g of x from 0 to 9 is 27.6. In Part C, the student needs to find the area of the region R, and this region is described in the statement of the problem and illustrated in the given graph. Here are some key concepts that we'll need in order to answer this question. This problem involves an application of the definite integral. Suppose the function f is non-negative and continuous on the interval a to b. The definite integral of f of x from a to b can be interpreted as the area of the region bounded above by the graph of f, below by the x-axis, and between the lines x equal a and x equal b. And in this case, we usually say that the definite integral represents the area under the curve y equal f of x from a to b. And while we're here, I think we should look at this application a little more generally. Suppose f is continuous on the closed interval a to b, and it takes on positive and negative values over this interval. Then the definite integral of f of x from a to b can be interpreted as net area. And that means that the definite integral represents the area of the region above the x-axis and below f, minus the area of the region below the x-axis and above the graph of f. Here's an illustration of these two concepts or applications. In this graph, f is non-negative and continuous on the interval a to b. The definite integral of f of x from a to b represents the area of the shaded region labeled R in the figure. In this graph, f is continuous on the interval a to b, but it takes on both positive and negative values. The definite integral represents net area. In the figure, it's the area of the blue shaded region minus the areas of the two green shaded regions. Now, although I won't go into this here, one can justify this interpretation analytically by considering Riemann sums. So, the issue we have now is that the definite integral can be used to represent the area of a region, but we don't have a method yet to actually find the area, or rather, evaluate the integral. Therefore, in order to solve this problem, we'll also need what I will call Part 2 of the Fundamental Theorem of Calculus. This says that if f is continuous on the interval a to b, then we can evaluate the definite integral of f of x from a to b by first finding an antiderivative capital F, and then simply subtracting capital F of b minus capital F of a. It's a pretty amazing result. Okay, let's put all of these ideas together to solve this problem. Here's a slightly modified graph of the one given in the question. We need to find the area of the shaded region R. We can see that the values of g prime of x are non-negative over the interval 0 to 9. The graph certainly suggests that g prime is continuous, but we also know that g prime is differentiable, so g prime is continuous on the interval 0 to 9. Therefore, the area of the region R is represented by this definite integral. An antiderivative of g prime is g. So, using the Fundamental Theorem of Calculus Part 2, this is g of 9 minus g of 0. And these two values were given in the statement of the question. So the final answer here is 19. Here are the scoring guidelines for Part C. This problem was worth 3 points. The first point is for representing the area of the region R with the correct definite integral. The second point is for correctly applying the Fundamental Theorem of Calculus. And the third point is for the final answer. And remember, a final numerical answer does not need to be simplified. Here are some interpretations of these guidelines to help understand how points are earned. The first point is a conceptual point and is earned for the correct presentation of the definite integral that represents the area of the region R. If the student presents a definite integral with incorrect bounds, they do not earn the first point. And they must present a definite integral to earn the first point. An indefinite integral does not earn the point, but the student is still eligible for the second and third points. And we tend to be a little forgiving on some notation issues here, under the pressure of a high-stakes exam. In this first definite integral, the differential dx is missing. And in the second, notice that there are mixed variables, t and x. However, both of these presentations would probably earn the first point. The second point is earned for correctly applying and sufficiently conveying the Fundamental Theorem of Calculus. Here are some examples that earn the second point. This example does not earn the Fundamental Theorem of Calculus point. The integrand is incorrect. To earn the third point, the student must use the values of g of 9 and g of 0. In other words, they cannot leave their final answer in terms of g of 9 and g of 0. Here are some example responses and how each is scored. The first example is the minimal response in order to earn all 3 points. Even though no definite integral is presented, there's enough evidence of the Fundamental Theorem of Calculus, and the final numerical answer does not need to be simplified. Remember, the scoring guidelines are for awarding partial credit. In this example, there's just enough presented for the answer point, but that's it. There is no evidence of the definite integral and no evidence of the Fundamental Theorem of Calculus. And we certainly understand that some students are able to compute the final answer right away. However, remember, we're stressing good communication and notation skills. So this response of a single 19 does not earn any points. And here's an example in which an indefinite integral is presented. The student does not earn the first point, but does earn the second and the third. In Part D, the student is asked to write an expression that represents the perimeter of the region R, and they don't have to evaluate this expression, which involves a definite integral. Here's the key idea here. We'll need to use the formula for arc length in order to answer this question. If f prime is continuous on the interval a to b, then the length of the curve y equal f of x from a to b is given by this definite integral. You may recall that we can actually derive this formula by first estimating the length of the curve using polygonal paths, and then we can examine the limit as n goes to infinity. And here's the same formula using Leibniz notation. Here is a solution to this problem. In the graph, the region R is shaded blue, and the perimeter is shaded green, and we need to measure the perimeter. And the way that I'll solve this is I will break the perimeter into 3 parts. The perimeter of the region R is the length along the y-axis plus the length along the x-axis plus the length of the curve y equal g prime of x from 0 to 9. The lengths along the y and the x axes are easy to compute. They're just straight line distances, 1 and 9. We can conclude from the graph of y equal g prime of x that g double prime is continuous. Therefore, the length of the curve y equal g prime of x from 0 to 9 is given by this definite integral. So the perimeter of the region R is 10 plus the value of this definite integral. Here are the scoring guidelines for Part D. This problem was worth 2 points. The first point was for using the definite integral for arc length in the computation of the perimeter. And the second point was for the final answer, the expression for the total perimeter of the region R. Here are some interpretations of these guidelines to help understand how points are earned. The first point is for the correct definite integral, so the correct bounds must be included here. The second point is for the final correct expression for the total perimeter of the region R. If the student presents an indefinite integral, even if the correct distances along the x and the y axes are used, no points are earned. Similarly, if an incorrect definite integral is presented, that is, either incorrect bounds or an incorrect integrand, then no points are earned. And there is an eligibility criteria here for the second point. The student must earn the first point to be eligible for the second point. In Part E, we need to determine if there is a value c between 0 and 9, such that g of c is equal to 0. And of course, we need to justify the answer. The key concept needed to solve this problem is the Intermediate Value Theorem. Suppose f is continuous on the closed interval a to b. Let n be any number between f of a and f of b, where f of a is not equal to f of b. Then there must be some number c in the open interval a to b, such that f of c is equal to n. Let's take a closer look at this theorem. First, here's an interpretation in words. It says that if the conditions are satisfied, then f takes on every value between f of a and f of b. The theorem says that there is at least one value c. There could, of course, be more than one. And this is an existence theorem. That is, it guarantees the existence of a value c, but it doesn't tell you how to find it. And I think we should note that the IVT is not necessarily true if the function is discontinuous anywhere in the closed interval a to b. And here are two graphs to illustrate the conclusion of the IVT and what could go wrong if the function is discontinuous. In this graph, the function f is continuous on the interval a to b. Therefore, for any value n between f of a and f of b, there must be a value c between a and b, such that f of c is equal to n. This illustration shows f of a greater than f of b and one such value c for the selected value of n. In this graph, the function f has a point of discontinuity in the interval a to b, so the assumptions for the IVT are not met. So that means for a selected value of n between f of a and f of b, there could be a value of c, so that f of c is equal to n, but we're not guaranteed that there is one. And this illustration shows there is no value of c for the selected value of n. Here's a solution to this problem. We're given that g is differentiable. Therefore, g is continuous on the interval 0 to 9. Next, notice that 0 is between g of 0 and g of 9. Therefore, by the Intermediate Value Theorem, there must be at least one value c in the open interval 0 to 9, so that g of c is equal to 0. Here are the scoring guidelines for Part E, and this problem was worth 2 points. The first point is for stating the conditions necessary to apply the Intermediate Value Theorem, and the second point is for drawing the correct conclusion using the IVT. Here are some interpretations of these scoring guidelines to help understand how points are earned. The student must establish, convey in some manner, that the function g is continuous. Now, the most common response here in this type of a problem is differentiable implies continuous. Perhaps not the best English, but the concept is conveyed. Now, this point is subtle. The student must clearly indicate that differentiability implies continuity. It is not enough to say that the function g is differentiable and continuous. If continuity is mentioned but not really established, and therefore the student does not earn the first point, they are still eligible for the second point. Some students in a problem like this will cite the mean value theorem instead of the intermediate value theorem, and use of the MVT does not earn the second point here. To earn the second point, the student must convey an appropriate inequality involving zero. And this can be presented in words or analytically. And here are two of the most common examples. And finally, the second point also requires an answer of yes, or some indication that there is indeed such a value c. I hope this video gives you a good idea of how to solve these problems using the necessary AP Calculus concepts and a reasonable expectation of how they would be scored. We'll look at more parts of this free response question in the next video.